Artificial Intelligence, Machine Learning, and Tiny ML at Pima Community College, presented by Neil Bungard, instructor in aviation technology. As a result of rapid advancement in technologies and a changing landscape in education, the role of learning institutions like community colleges is evolving. Community colleges are no longer just a segue to four-year institutions, and they are increasingly finding themselves as suppliers of talent that work directly with advanced technologies. Machine learning is an advanced technology that is particularly suited for development at the community college level. Being an instructor in aviation technology, I will tend to focus on aviation examples, but keep in mind that machine learning is a universal tool and can be used by any discipline. Aviation applications like guidance, control, and information acquisition and processing have classically been handled by statistical classification and modeling techniques, open and closed-loop control algorithms, and standard curve-fitting routines. Machine learning offers a reasonable alternative to traditional analytical approaches in system design and evaluation environments that are data-rich but lack a clear analytical solution, such as pattern recognition and adaptive monitoring and control. In addition, machine learning works well in environments where data may be plentiful but may be incomplete or noisy, such as in sensor processing, predictive analysis, and guidance. Furthermore, modern machine learning development environments can be utilized by the investigator without the need for a data scientist or a machine learning engineer. Faculty members at universities, science and technology centers, and community colleges find themselves in a unique position to develop and implement custom solutions to their problems using machine learning techniques. When would machine learning be used over classical analysis solutions for solving a problem? Many problems are better solved with a classical analytical approach. These problems usually have a finite number of input variables and exhibit a clear relationship between the input variables and the solution. A problem that might be better suited for machine learning may have a larger number of input variables, and the input variables may contain interdependencies. Furthermore, the solution is not obvious by looking at the input variables. An example of an analytical problem might be diagnosing why an automobile fails to start. Either the automobile is not getting the proper amount of fuel at the right time, or it is not getting sufficient spark at the right time. There are a finite number of systems components to check, and a program could be developed to systematically check the operation of each system component until the problem is located. Contrast the automotive problem with a problem like face recognition. There are millions of unique faces, and there are thousands of measurements, colors, expressions variations, angle detections, lighting conditions, etc. It would be impossible to write a program to take all of these input variables into account. And there is certainly no direct correlation between the variation of input variables and any particular face. This problem is perfect for machine learning. How does machine learning work? Let's say that you needed an application that can identify a particular aircraft type. Furthermore, you need the detection to occur at the camera that is viewing the object. Possibly a camera on a drone. An analytical solution would not work well for this application. There are too many different aircraft types and thousands of features defining each aircraft. As shown in Figure 1, using machine language to solve this problem, two things will be needed. First, many examples of aircraft types and many examples of each type will be needed. Secondly, the type of aircraft that represents each example will be needed. Pixelizing the pictures of each aircraft type will result in the creation of an input variable matrix that represents each aircraft type. Using these matrices and the known aircraft types for each aircraft, a machine learning algorithm is trained to identify each aircraft type. The machine learning algorithm learns the relationship between each input feature matrix and a particular aircraft. It is not programmed to perform this identification. It learns to identify the aircraft types on its own. The second requirement of this example is that the collection of aircraft examples, training of the machine learning algorithm, and detection of aircraft types are performed on the drone camera, referred to as machine learning at the edge. This makes this application not only a machine learning solution but also a tiny machine learning solution. What is Tiny ML and why is it increasing in popularity? TinyML is a type of machine learning that shrinks machine learning networks to fit on tiny hardware, which is then fitted to the application of interest. This tiny hardware is ultra-low power embedded devices, and they are invading our world. With new embedded machine learning frameworks, TinyML will enable the proliferation of AI-powered IoT devices. Figure 2 shows just a few of the applications that TinyML is currently being used for. The advantages of using TinyML as a problem-solving tool include 1. Fast inference with low latency. Edge devices can process data and provide inference with low latency because no server is required. 2. Low power consumption. Microcontrollers consume very little power. 3. This enables them to run without being charged for a long time. 4. Data privacy. Sensitive data is not compromised because data does not leave the edge device. 5. Doesn't depend on connectivity. Smart edge devices can make inferences without an internet connection. Of all of the advantages of TinyML, the most interesting and relevant advantage is that machine learning development environments are being simplified and automated. This is an important concept because it moves the development of the TinyML application away from the data scientists into the hands of the subject matter experts, the end users. We will no longer need knowledge engineers to interface between the subject matter experts and the machine learning developer. The subject matter expert will be the machine learning developer. This will make the development process more efficient and less expensive, and will enhance creativity in the problem-solving process. More importantly, it will enhance the role of the universities, science and technology centers, and community colleges because this is where the subject matter experts reside. Why is TinyML a perfect technology to be developed and implemented by universities, science and technology centers, and community colleges? A great deal of research and technological investigation is being conducted at universities, science and technology centers, and community colleges by subject matter experts. A factor that makes their investigations possible is the fact that the analysis tools have become smarter, allowing the subject matter experts to conduct their investigations without being an expert in the technologies of the analysis tool itself. Such is the case with machine learning and TinyML in particular. If an individual is an expert in a particular subject and has a familiarity with embedded computing and machine learning concepts, she can use these technologies to discover new and exciting information in their field of study without the need of a data scientist or a machine learning engineer. This opens the door for faculty members in any field of study to conduct research or development using these new state-of-the-art technologies. Community colleges are positioned to take advantage of the emerging environments in technology and education. What is needed is an environment within the community college that can focus on advanced technologies and enables faculty members to create programs that provide industry with the talent that they need. Thanks for watching.